Welcome in. All right, so here's a couple of examples, or here are a couple of examples for you with regards to standing waves. Now, I'm going to assume, okay, that you're semi-familiar with standing waves and you understand harmonics, okay, so that's what you have there, okay. You have kind of lambda, which are the wavelengths, frequencies, okay, so those are things that you are familiar with. Now, if you want an introductory standing waves kind of concept video, which talks about where they're actually coming from, what's happening, okay, that I will link up above there for you. All right, here I just want to give you some examples on how to do calculations with regards to some standing waves. So the first example that you have is, it states a guitar is played with the fifth harmonic on a string length of 65 centimeters. All right, so as you take a look at this, so if it's a guitar, and this is exactly, okay, where these standing waves might be useful, and this is one of the reasons why we can generate such beautiful music. And a guitar has two fixed ends, all right? So that's the first thing that we would want to be able to note for ourselves. Now, if it has two fixed ends, it's going to have a certain formula, okay, with regards to the actual comparison between the length of the string, okay, and lambda. So you may recall, and if not, you can certainly kind of look it up. There are two particular formulas. So here they are. So the formulas that we have, okay, within here, so I've noted it up. This relates back the length, okay, to your actual wavelength overall for each of the harmonics. That's what the N stands for. Now, there are two equations. This first one is related to fixed ends and open ends. And then this second one is related to a fixed end and an open end. Okay, so meaning one is fixed, one is open. Okay, the first one is when both ends are fixed or both ends are open. So we're going to be using this equation for this example. All right, so if I'm going to kind of copy it down, now it's talking about the fifth harmonic. So this is L5 is equal to, and now we have 5 times our lambda divided by 2 within here. Notice that the length is 65 centimeters. So be careful, try to change it back to standard metric SI units. So 65 centimeters is going to be 0.65 is equal to 5 lambda divided by 2. And now we can find out what the wavelength is. Now, let's continue and see what they want out of this question. If the speed of sound in the string is captured at 180 meters per second, okay, so that would have been the speed, which is 180 meters per second. So meters per second is in metric standards. Now, recall that this is going to be related to the fundamental wave equation, which captures both frequency and your wavelength, okay, of an actual wave. So we have these two, okay, within here. Now, I know that it's 180 for the speed. Now, they want us to find out what the frequency is. All right, so we want to be able to find this. So let's jump in here. I can certainly find out what lambda is, okay, within there. So I can certainly do that, okay, as you're going through. So I'm going to work this out right here. So this is going to be 0.65, notice multiplied by 2 and divided by 5, which is equal to lambda. So that's that. And once you have this, you can substitute it in here. And you can then solve, so it's going to be 180 divided by this lambda to find out what the frequency is. All right, so let's do that on a calculator. So I'm going to pop this up. Okay, let's shift it over. And let's see what this is. So 180 divided by, I'm going to put all of that in brackets so I don't have to do the multiplication, do the computations twice. It's going to be times 2 and divided by 5 equals. All right, so that's the frequency within here. So frequency F is equal to, so it's about 692. Now we can round this off. I mean, I guess this has two significant figures the most. Okay, so we can just kind of round it off approximately at 690, and this would have been hertz because everything else was in metric standard units. So that's one example with regards to standing waves. Let's take a jump at a second example. So here it is. So for a standing wave, Now, with one fixed end and one free end, so this is important to note. So one, okay, fixed end and one free end, which means, okay, so if I jump back in here, we're going to actually be using now this equation right here. So I'm going to copy this down. So, and bring it back down here. No, that's okay. I mean, that's fine. Okay, I'm just going to concentrate on this equation right there. The other one is not the one for this example. Now, the third harmonic, so this is again, so this would have been n is equal to 3, is to be produced. The speed of the wave is to be set. So the speed of the wave is 420 meters per second, right there. If the frequency of this wave is, so my frequency is 250 hertz, then what should be the expected length? All right, so we want to know this. We want to know what is the actual length within here. So let's see. Well, just directly from here, I'm going to find out, so that, remember, V is equal to, so this is frequency times lambda. I can find out lambda in here, no problem, because that's going to be V over F. So I have my lambda within there, and those calculations for lambda is 420 divided by 250. Now, once I have that lambda, I can substitute it back into here, okay, to find out the rest. Now notice, so as you're working this out, so this is going to be my length, okay, so this is the third harmonic, is equal to, so this is going to be 2 multiplied by 3 minus 1 divided by 4 times the lambda, well, lambda is 420 divided by 250, right there. So now if you substitute all of this back in, okay, you'll have your answer. So what's in bracket there is rather easy on the left. So it's going to be 6 minus 1, which is going to be 5 over 4. So this is just 5 over 4 multiplied by all of this. So let's punch this into the calculator to get our answer. All right, let's clear this up. Okay, so 5 over 4 and times, and then again, so this is 420, okay, all over 250 equals, and so this is going to be 2.1. And this would be in meters. All right, so that's the length that we would need in order to make this happen. So there you go. So you have two examples. Now you can see that the calculations, hopefully, for these kind of standing waves are not that difficult. It's probably much more, or at least it's harder to understand the concept of standing waves. The calculations themselves, okay, are relatively simple. Thanks for watching. I hope that you found this useful. See you in a future video. Bye, everybody.